Now that we've built up an understanding of entropy, we're prepared to make another big jump, which is to define the Gibbs free energy. And what this is, it's the amount of energy which is available to do useful work. So for example, how much energy we could extract out of a battery, or how much energy would come from some hydroelectric system powered by a waterfall. And there's a condition for this, actually two conditions. We have to be at constant temperature and we have to be at constant pressure. And if we are, then this is the formula that tells us the value of the Gibbs free energy. So we take the enthalpy and we subtract the temperature times the entropy. That tells us how much energy is available. Now, if we have a physical or a chemical process where we are changing states of the system, then our change in Gibbs free energy is going to be equal to the change in enthalpy minus the temperature. Remember, temperature can't change. We have to have constant temperature for Gibbs free energy, times the change in entropy. Now, the universe likes to minimize its energy. So, if we do minimize the energy for a process, so delta G is negative, then that process is going to be favored by the universe, and it's just going to happen spontaneously. Now, what that means is going to happen without our intervention. So, for example, wildfire, once the fire gets going, that's a spontaneous process. It's going to spread through the forest. We don't have to supply any extra energy of our own to make that happen. But a caution here, spontaneous does not mean rapid. A spontaneous process can take a very long time to occur. So actually, even though once we have a spark, we're going to accelerate that combustion process, if we were to just leave a log out in the presence of oxygen, that oxygen will react with the log. It will just take a very long time for it to do it. So we might have to wait 1 million years for it to happen, but it's still spontaneous for that reaction. Now, if our available change in free energy is 0, that means there's no difference between our initial state and our final state. That means we're at equilibrium. And finally, if delta G is positive for some change, that must mean we have to throw energy into the system in order for it to proceed, and in order for that reaction, that process to actually occur. So it's not going to be spontaneous, it's going to be non-spontaneous. However, it will be spontaneous in the opposite direction, because the opposite direction would be going from a high energy state to a low energy state. Now, a few examples of these situations. If we were to drop a book, I think we realize that's going to happen spontaneously. We can also think of it, we're going from a high energy state to a low energy state. So our change in Gibbs free energy is going to be negative. We're going to reduce the amount of energy available to us. If we wanted to power a light bulb, in this case we're going to have to supply energy to the system to drive it forward. So in this case, delta G is going to be positive. If we were to consider something like the motion of well-mixed gas molecules, even though they are moving around, our system never changes if they're well-mixed. We're always going to have a very highly entropic system where everything is equally dispersed. And so that's an example of dynamic equilibrium. And so our delta G in that case is 0. There's no energy available for extraction. Well, how about if we want to find an actual numerical value for delta G? Example where we might do that, we could figure out the amount of energy available in an AA battery. So alkaline batteries undergo this reaction, or at least some of them do, where zinc reacts with manganese oxide to produce zinc oxide and manganese oxide. And let's say that there are 5.4 grams of zinc in this AA battery. How much energy is available? How much work can this battery feasibly do by undergoing this reaction? Well, what we were trying to find is delta G for the reaction, and we know the expression for delta G is delta H minus T delta S. And I'm going to assume we're at standard conditions here so that we can look up this information in a table, which is going to be tabulated under standard conditions. So that means 1 atmosphere pressure for gases, 1 molar concentration for aqueous substances, and our temperature is going to be whatever it's defined for in a table, which is usually 298 Kelvin. So I'll go ahead and look up the enthalpies of formation and the entropies so that we can calculate the delta S and the delta H and plug them into this equation. So went ahead and looked these all up for these substances. Note that zinc is an element in its most common stable form, so you're actually probably not going to find its enthalpy listed because it's expected you just know that it is 0 for elements in their most common stable form. Now we can start finding the delta H and the delta S for the reaction. So remember, we take the sum of the products minus the sum of the reactants in each case, and we need our stoichiometric coefficients. So in this reaction up here, we have 1 of these, 2 of these, 1 of these, and 1 of these. So those are the coefficients I'm building in right here. So take our products, which are zinc oxide and manganese oxide, minus our reactants, which is the zinc and the manganese oxide, and plug all those numbers in, get minus 267 kilojoules per mole. Then I'll do the same thing using these entropy values over here for our entropy equation, and get 6.6 joules per Kelvin mole. Now, note here that this is in kilojoules and this is in joules, so if we want to be able to combine these, we're going to have to convert one. Well, now let's go ahead and plug in, now that we've calculated the delta H and the delta S value. And remember, since one's in joules and one's in kilojoules, we'll go ahead and convert this one into joules. Another point is that since we're at the standard state, our temperature is going to be whatever our values were tabulated for, which is usually 298 kelvins. So we just have to know to stick 298 in here. And we crunch that, and we get a delta G for this reaction of minus 269 kilojoules per mole. And then the very last step is to get rid of that moles by doing some dimensional analysis. So we had 5.4 grams of zinc, and 1 mole of zinc weighs 65.38 grams, and our reaction is written for just 1 mole of zinc. So we multiply it all out, and we find that we have a total delta G here of minus 222 kilojoules. So this is the theoretical maximum of energy in your battery. Now, will you actually get this much energy out of your battery? Well, no, because all of the zinc is not going to react. And batteries have internal resistance, and there's going to be other reasons why you can't extract all of this energy. But this gives us a maximum value. Now we can also ask the further question, what direction does this reaction proceed? Well, since delta G is negative, we know this reaction is going to be spontaneous in the forward direction, and so we're going to produce products at this point. Just like for enthalpy and for entropy, Gibbs free energy is a state function, which means that in order to figure out the change in Gibbs free energy over a process, we just need to know the starting Gibbs free energy and the final Gibbs free energy. And it doesn't really matter what path we take in between them. So one way we could do that is we could measure the total Gibbs free energy of the reactants and the total Gibbs free energy of the products, and the difference between those would be the change over the course of the reaction. And unfortunately, just like with the enthalpy, we don't actually know this point where our Gibbs free energy is equal to 0. So we don't actually know how much energy is in our reactants or how much energy is in our products. To calculate it, we'd have to take into account all the nuclear forces and the electric forces, and we'd have to do it for all the atoms and molecules in our system, and it would just be too complicated. So what we do instead is we can measure this difference from any initial position, and we just define a different position where everything is an element in its most stable form, and we say that this has the value of 0. And so then instead of measuring this difference and this difference, we'll measure this difference and this difference. But the difference between those two will still be our delta G of reaction. And so just like with enthalpies, whenever we have elements in our most common stable form, we're going to give them a delta G of formation of 0. And then for any other substance, we're going to define a delta G of formation for it relative to these elements up here. And that can be represented by this equation right here. It says take this difference right here, and that will be our delta G of reaction. And then just a reminder again that this little circle here means that our information was tabulated with everything in 1 atmosphere pressure, 1 molar concentration, and 298 kelvins of temperature. So let's go ahead and revisit the example we did earlier, where we're trying to figure out how much energy is available in an alkaline battery that has 5.4 grams of zinc in it and undergoes this reaction. And this time we'll do it the easy way. So we'll go ahead and directly calculate the change in Gibbs free energy of reaction just by using the Gibbs free energies of formation. So we'll have to look those up, and we'll do it for all the substances. And again, zinc, we might not find it listed because it might just be assumed that we know that it's 0 for an element in its most common stable form. And then we will go ahead and plug our delta G values into our equation. Take the delta G's of formation of the products minus the delta G's of formation of the reactants. And we get the same number, negative 269 kilojoules per mole. But this was a little bit less work than our other calculation. And then again, we multiply that by the total number of moles of zinc to get our total energy change for this particular reaction. Something else we can do is make qualitative predictions about delta G. And as long as we can make those predictions for delta H and delta S, then we can just plug them into this equation and know what the value of delta G is. And that's wonderful because then we can intuitively know whether a reaction is going to be spontaneous or not. So let's put these values in a table here. So if we have a negative value for delta H and a positive value for delta S, well, a positive value for delta S is going to give this term right here, this negative T delta S, a negative value. Remember, T is measured in Kelvin, so it's always positive. So we have a negative number times a positive number times a positive number gives us a negative number. And then when we take a negative number minus a positive number, then we're going to have an even more negative number. So since delta G is negative in this case, we're going to have a spontaneous reaction. Conversely, if delta H is positive and delta S is negative, well, if delta S is negative, we throw that value in here, then we'll have a negative times a negative, which is a positive times a positive, so we get a positive value. So we wind up with a positive plus a positive. That's going to be non-spontaneous since delta G is positive. Now, our last couple of cases, it could be that our delta H term is negative and our minus T delta S term winds up being positive because delta S is negative. So what answer do we get when we add a negative to a positive number? Well, we don't know. That's going to depend on the magnitude of our answer. Same thing if delta H is positive and delta S is positive. We're still going to get an ambiguous answer. It's going to depend on our magnitudes. Well, the only thing that's varying here is the temperature for a given reaction. And so if the temperature is very large, then this term will dominate. And so if this term is positive, the whole thing will be positive. If this term is negative, the whole thing will be negative. Conversely, if it's very small, so maybe T is equal to 0 here, then the only thing that's going to affect the value of delta G is delta H. So we can write that we are going to have a spontaneous reaction in this first case if the temperature is very large. And in the second case, we'll have a spontaneous reaction only if the temperature is very small. So for example, let's say we want to predict whether the exothermic reaction, where we have nitrogen react with hydrogen to produce ammonia, is going to occur spontaneously, all by itself. We just stick the nitrogen and the hydrogen in a container, and we wait some time and we'll detect some ammonia has been generated. Well, we're going to apply our delta G equation, and to do that we need to figure out signs for delta H and delta S. So delta H is going to be negative because this is an exothermic reaction. Delta S is going to be negative because we go from having 4 moles of gas to having 2 moles of gas. So that's a net decrease in entropy. We're going to give it a minus sign. Now, if we stick a minus sign in for delta H and a minus sign in for delta S, these two minuses are going to multiply and become a positive. So we're going to have a negative number plus a positive number. So that's going to be ambiguous. It could be a negative result or a positive result, but it will be a negative result as long as this T is very small, because then this negative number will be the significant one. So we're going to say that this reaction is going to occur spontaneously as long as we're at a low temperature. Now, what if we want to know our Gibbs free energy for some process that occurs at a temperature that isn't 298 kelvins and doesn't have gases at 1 atmospheric pressures and substances at 1 molar concentrations? Well, in that case, we just need to calculate the standard Gibbs free energy and plug it into this equation. R here is the gas constant. And since we're doing energies, we probably want to use the 8.314 joules per Kelvin mole version. And then we have our temperature, which we want to have in kelvins, and multiply that by the natural log of the reaction quotient from the reaction. Remember, if there's no change in the number of moles of gas, then the reaction quotient is for the gas is the same thing as for concentrations. As an example here, let's go ahead and compute this for our Haber process reaction, where we have N2 react with hydrogen to produce ammonia. And let's say that we're doing this at 298 kelvins, that the present pressure of the nitrogen is 1 atmosphere, the pressure of the hydrogen is 3 atmospheres, and the pressure of the ammonia is 0.5 atmospheres. So what's the amount of energy available under these conditions as this reaction is allowed to proceed? Well, so we're going to apply this equation that we just stated. So we just need to calculate the pieces for it. We can calculate delta G by the usual way. And I'll skip throwing the numbers in, but if you look up the numbers in a table and plug them in for the Gibbs free energy formations, you should get about negative 33 kilojoules per mole for this reaction up here. Now let's calculate QP. So for our reaction, we're going to do products over reactants, and products are going to be squared. Reactants, N2 is first order, H2, that's going to be cubed. So pressure of ammonia squared over pressure of N2, pressure of H2 cubed, and then just plug in the numbers, and we get 9.3 times 10 to the minus 3. All right, so now we can just plug into our equation. So go ahead and do that and come up with a value of negative 44.9 kilojoules per mole. So this is how much energy we're going to get out of our reaction when we perform it at these pressures. And you can tell from the minus sign that this must be something that will happen spontaneously under these conditions.